Hello, dear all classmates. Today we are going to talk about Boolean testing without four models. In our previous lecture, we have studied many different test techniques using four models such as stopgap faults, transition faults, and so on. But sometimes we don't need any four model to test the circuit. For example, exhaustive test and the pseudo exhaustive test. Today we are going to introduce pseudo exhaustive test. We all know that exhaustive test is a very effective test method. In exhaustive testing, we apply all possible input combination to the circuit. For a combinational circuit with n inputs, the test length is 2 to the power of n. There are many advantages for an exhaustive test. First of all, we don't need any ATPG tool to generate patterns. Second, we don't need any fault simulation. The fault coverage is guaranteed to be very high. And it's suitable for bits because we don't need to store any patterns on the ATE. And we don't need circuit multiplication such as DFT. And the fault coverage is very high. However, the disadvantage, of course, is that the test length is too long. Do we really need all the 2 to the power of n test patterns? Actually, we don't. Pseudo-exhaustive test, or PET, was proposed by McCluskey in 1984. The idea is that we actually do not need exhaustive test for the whole circuit. We can just partition the circuit and test each partition exhaustively. There are two categories of PET. In the first category, individual output verification, or IOV, we partition the circuit into logic cones. We just simply test each logic cone exhaustively. If we test all the logic cones, then we test the whole circuit. The second category is the segment verification. In segment verification, we partition the circuit into segments. If we can test each segment exhaustively, then we test the whole circuit exhaustively. So this is the idea of segment verification. Now, let's introduce individual output verification. In individual output verification, we apply all possible input combinations to each individual output. For example, in this circuit, the input cone of output O1 has N1 inputs, and the input cone of output N2 has N2 inputs. If we want to test the circuit exhaustively, we totally need 2 to the power of N1 plus N2 test patterns. Suppose that there is no overlap between N1 and N2. However, we don't actually need so many patterns. We can simply test the first cone exhaustively, which takes 2 to the N1 patterns, and we test the second cone exhaustively, which takes 2 to the power of N2 patterns. Then we just need 2 to the power of N1 plus 2 to the power of N2 test patterns. So IOV can greatly reduce our test length. We can simply classify our circuits into PDC and FDC. In PDC, partial dependent circuit, no output depends on all the inputs. In this case, IOV can be applied to reduce the test length. FDC, or full dependent circuit, has some output that depends on all the input. as shown in this figure. A certain output depends on all the input. In this case, we cannot apply IOV to reduce the test length. For example, this is a simple circuit 74LS630. In this circuit, it has 24 inputs and 6 outputs. Each output depends on 10 inputs. So if we want to exhaustively test the circuit, it would take 2 to the power of 24 test patterns. If we just test each output exhaustively, the test length is simply 6 times 2 to the power of 10, which is much smaller than the true exhaustive test. For a second example, 71181 ALU. This is a 4-bit arithmetic logic unit. This is the first ALU on a single chip. It was used as ALU core in many CPU. It has 14 inputs, 8 outputs, and the sum output depends on all the input. In this case, IOV cannot be applied to reduce the test length. To derive the IOV test, we need to first find the dependency matrix. In the dependency matrix, each row corresponds to an output. Each column corresponds to an input. For example, in this circuit, F is dependent on input V and X, so the corresponding entry in the dependency matrix is 1. F is not dependent on input Y, so the corresponding element in the dependency matrix is 0. For each row, we take the summation of the row, so we have row weight. Among these row weight, the maximum row weight is denoted as W, which is equal to the maximum output dependency. That means the maximum number of inputs connected to an output in the circuit. For this example circuit, W value is equal to 2. And then we partition the dependency matrix such that each row of a partition have at most 1 in this partition. For the previous example, given this dependency matrix, we partition this matrix into 3 parts. In the first partition, we have input V. In the second partition, we have input X. In the third partition, we have inputs Y and Z. Please note that in each row, there is at most 1. For this matrix, we have 3 partitions. P denotes the number of partitions. The smaller P is better, because smaller P corresponds to fewer number of test inputs. Please notice that PDM is not unique. We can also partition this matrix into only 2 partitions, where VY is a partition and the XZ is a partition. Of course, smaller P is better. In this partition, we only need 2 test signals, so our test length is shorter. Given this partition where P is 2, we can assign 2 test inputs to each partition. For the first partition VY, we assign test input T1. For the second partition XZ, we assign a second test input T2. To test the output F exhaustively, we can apply only 4 test patterns. To test the output G exhaustively, we can also apply 4 test patterns. To test output H exhaustively, We also only need 4 test patterns. So the maximum number of input connected to any output is equal to 2, and the minimum test length is 2 to the W, which is 4. This is another real example for the IC 74630. It has 24 input, 6 outputs. If we calculate the row weight, the row weight for each row is 10. And then we partition this matrix into 10 partitions. In each partition, there is at most 1 1 in each row. To test this circuit exhaustively, we would need 10 test signals. When we apply IOV test, what is the minimum test length? The answer is 2 to the power of P, which is 2 to the power of 10. A minimum IOV test means the shortest IOV test to test a circuit. The minimum IOV test length must be equal to or greater than 2 to the power of W. The test length cannot be lower than 2 to the power of W. Why? Please think about it. There are 3 possible cases. In the case 1, where P is equal to W, then the minimum IOV test length must be 2 to the power of W. This is always true. In the second case, when P is equal to W plus 1, in this case, the minimum IOV test length is also 2 to the power of W. This is also true. We will show that later. In the third case, where P is greater than W plus 1, minimum IOV test length can be equal to or greater than 2 to the power of W. We may or may not achieve the lower bound 2 to the power of W. It is case dependent. We will show that later. In the first case, where P is equal to W, we have seen this case earlier. In this case, P is 2, W is also 2. So the minimum IOV test length is 2 to the power of W, which is 2 to the power of P, which is 2 to the power of 2. In the second case, where P is equal to W plus 1, the minimum IOV test length is equal to 2 to the power of W. This is always doable. Given W test signals T1, T2, and TW, we can exclusive OR them to generate the next test pattern TW plus 1. So we have this equation. For example, given a circuit where P is equal to 3 and W is equal to 2, like this example, the row weight is 2. And we have 3 partitions, 1, 2, and 3. Given this circuit, we can always assign Z equal to X exclusive OR Y. So we have these 4 test patterns. If you take X and the Y, this 4 test pattern is exhaustive. Or if you take Y and the Z, they are also exhaustive. If you take X and the Z, these 4 test patterns are also exhaustive. No matter which pair you take, you always get an exhaustive test. So this is a valid IOV test. In the third case, where P is greater than W plus 1, we may or may not achieve the lower bound. For this particular example, where P is equal to 5 and W equal to 3, the minimum IOV test length is 8, as you can see in this picture. For example, for F1, which depends on UV and X, this is an exhaustive test. For F8, the inputs are X, Y, and Z. This is also an exhaustive test. You can do a check by yourself. The remaining outputs are also tested exhaustively. However, in some other circuits where P is larger than W plus 1, the minimum lower bound may not be achieved. In this example, we have 6 outputs and 4 inputs. In this circuit, the minimum IOV test length is 5, which is greater than 2 to the power of W. You cannot find a shorter test than 5. So, what should we do to handle the circuit where P is greater than W plus 1? In this case, we can look up the table called Universal IOV Test Table. The Universal IOV Test Table provides a general solution for the circuit where P is greater than W plus 1. Please note that the test length of the solution provided in this table is greater than 2 to the power of W. This might not be an optimal solution. In this table, the notation Uij represents a p-column matrix where we produce all the possible weight I and all the possible weight J rows. For example, if we have a circuit where W is equal to 2, we can look up this table and we find 2 solutions. One solution is U0P-1. The other solution is U1P. So what does that mean? It means a row vector where all the row weight is 0. It also means all the possible combinations where row weight is 3. In this example, we have 1110, 0111, 1101, and 1011. The total test length is 5. If we apply this pattern to the circuit with 4 inputs, no matter which pair of the input you take, you always get exhaustive test. You can check by yourself. The second choice we have is U14, which means an exhaustive combination of vectors where the row weight is 1. So we have 1000, 0100, 0010, and 0001. And U4 means a row weight of 4. Again, the test length is also 5. When we take the combination of any pair of input, we always get an exhaustive test. You can check by yourself. So, according to the Universal IoT test table, we have got a general solution of which the test length is 5. This is larger than the lower bound, 2 to the power of W. Okay, you now know everything about the IOV test. Please do the following exercise. Given the following circuit of 6 inputs and 2 outputs, what is the value of P? What is the value of W? Please show that the minimum IOV test length is 32. Our question is that, can we do better? In the second part of the PET lecture, we will introduce the segment verification technique. In the segment verification technique, we can partition the circuit into segments, and we test each segment exhaustively. There are 2 possible techniques. We will introduce the path sensitization first. Given this circuit from the exercise, we can partition the circuit into 4 segments. Segments A, B, C, and D. Now we test the segment A exhaustively. It has 3 inputs, so the shortest test length would be 8. To sensitize node G to output F2, we need to set input Z to 1 all the time. Totally, we would need 8 patterns. And then we want to test segment B exhaustively. The input to segment B are Z and G. We will need 4 test patterns. 2 of them are already included in our previous 8 test patterns, so we just need to add 2 more. And then we want to test segment C exhaustively. Segment C has 2 inputs, U and V. We want to sensitize the output of the OR gate to F1. In that case, we would control G to 1. If we look at our previous test closely, we already have 4 test patterns where G is equal to 1. So we can squeeze in our test patterns without adding any extra patterns. Finally, we want to test the segment D exhaustively. Segment D has 2 inputs. If we look at our previous pattern, we already have 0, 0, 0, 1, and 1, 1. And we also have 1, 0. So we don't need any extra patterns. Totally, we have 10 patterns to test this circuit pseudo-exhaustively. You might think that, oh, test sensitization is a really powerful technique. But what if I am not smart enough to find the short test? We can use hardware solution to insert mux. Given the same circuit, now we insert 2 mux into this circuit so that we can control and observe this G. The penalty is that we need to insert 3 text signals, which are C1, C2, and T. And we need to insert 2 mux into the circuit. Your exercise is that please find out the minimum PET test length with these 2 mux inserted to the circuit. In summary, given this circuit, because we have 6 inputs, the exhaustive test will be 2 to the power of 6, which is 64 test patterns. Using the IOV test technique, the test length can be reduced to 22. Using the PET segment verification technique, we can reduce the test length to only 10. Also, we can apply the max insertion technique to perform PET tests. Using the PET techniques, the test lengths are greatly reduced compared with the original exhaustive test. Thank you for listening.